Assalamualaikum and good morning. So today we would like to enter chapter 2. So chapter 2 is about Hardy-Cross method. So this method will be used to determine flow rate for pipes network. So pipe network mean previously in fluid mechanics 1, we are focusing on one single pipe. So in one single pipe, you know that we could calculate its velocity, its flow rate by using the Bernoulli equation. Then at the same time, we need to determine the losses, means the friction, the major loss and the minor loss. Okay. However, in another application, so sometimes we have a network of pipes, means pipe with connected with other pipe and it create a network. So in network, we are capable to calculate the flow rate by using the Bernoulli equation, but we will have a lot of unknown. So mean, for example, we sometimes we will have 6 unknown. So mean you need to develop Bernoulli equation, 6 Bernoulli equation from 6 different points. Okay, so that's and then you need to solve it simultaneously, one by one, so it takes a long time. However, but to simplify this one, I would like to introduce you Hardy-Cross method. So that's what we will learn in chapter 2. Okay, but before that, I would like to give you, just to remind you a few things about this. So first, it is about the pressure drop and losses in pipe. Okay, in real application, sometimes if you discuss with water engineers, engineers who work with Shabas, who work with Renhill, SAJ Johor, so they will not talk about losses, but the keyword to represent the losses is the pressure drop. So why they are using pressure drop here? Because it based on the calculation. So for example, we have a one single pipe here. So we have point A and point B. We could develop Bernoulli equation as this one. So I think you already know how to develop this. And then in a real application, the pipe diameter is almost is the same, because it is not common for water supply contractor to have so much different diameter in pipe supply. So we are talking about the pipe system. The pipe system means to connect from the water tank in your taman, okay, and then distribute to all the houses and so on. Okay, it is not about the one small pipe in your house and so on. This is about the pipe system. So as you know, SAJ will use a specific pipe. So means that the diameter is not easily changed. They will use the same specification, okay, because they ordered that size in bulk. So the diameter is the same, so we could say that the velocity is remain constant along the pipe. So and then we could say that the velocity of A here and the velocity of B here, it can be cancelled out because the value is same. And then normally for sure they have the elevation, mean the height different. But in a big system, okay, in a system pipe, we could say that the height is almost the same, because they cannot install big pipe in totally different in normal application for the housing purpose, for the urban purpose and so on. So normally they will find a very straight plane, okay, to install, to build the pipe system. Okay, so and then in overall, from the overall point of view, we could say that the elevation, the height is the same. So again, the potential energy, which is ZB and ZA here, can be neglected. So we can cancel this value. So and then we could simplify this one into this. So I hope you could imagine how this equation can be, because it starts from the Bernoulli equation here. So we cancel the value of velocity A and B. We cancel the elevation, the height of Z A and ZB, and then we have PA, and then we bring the PB here to the left hand side. So it is equal to losses here. So this is what we get. That's why if you talk with the contractor who supply the water here, they will say the pressure drop, because the pressure drop will show the losses of that system. Okay, this is the reason why they will use the term of pressure drop. So, and then we need to discuss about the losses here. So, as we learned previously, losses here consists of major loss and minor loss. So, major loss is F L over D V square over 2G, and minor loss is K V square over 2G. And minor loss here is depend on the parts of the pipe system. If you have bending, if your pipe is so rough, and okay, you have bending, you have parts like decrement of pipe size, increment of pipe size, and then you have pump or turbine and so on and so forth. So this is the minor loss. And then this is the equation for my major loss. So we have F L over D V square over 2G, and F here is the friction factor. I hope you still remember how to determine the value of F here from the Moody chart. Okay, so and then to determine the F here, we need to know the epsilon over D. So this is the Moody chart, okay? And then I would like to tell you here, actually the Moody chart is the chart, the Moody chart is actually developed by one equation of this one. So this is the equation to get every line here. So you substitute everything and then you could plot here actually. So, but because this equation cannot simplify with only one single F on the left hand side, so the equation will remain like this. So, and then Colebrook and White work together. They are using try and error method actually. They try to fit in the numbers and so on and so forth. And finally, the Moody chart, okay, can be developed like this. Okay, actually Moody turned it into this diagram, but the research about this equation is actually led by Colebrook and White. Okay, so and then we would like to see the Moody diagram here. Okay, if you could see, so this is the laminar flow. So means that if you calculate your flow in pipe by using the Reynolds number rho Vd over mu, so if you get the value is less than 2000, mean it is fully laminar. So if it is fully laminar, you need to calculate the F, the value of friction factor, by using this equation. So which is 64 over Reynolds number. But for pipe network, so the diameter is very big, and for sure there are no laminar flow for the pipe network. So you may have laminar flow, it might be in laboratory scale or in your house pipeline. So pipeline means 1 inch pipe, so it can be laminar flow. It has possibility. So if you see the Moody diagram here, you could see that this line. So this line will show you the complete turbulence region. Means at this region, so we found that the flow is completely turbulent. Means that at this region, okay, it is actually the transition between laminar and turbulence. Okay, and in our fleet 1, we are focusing on this region. Okay, whether you realize it or not, so we actually ask you actually in this region, because this region is actually commonly occur at small diameter pipes. It means for if you have a water tank and then you connect your water tank with might be 1 inch or 1.5 inch pipe, so they are in a transition region. That's why in our fluid mechanics 1, we need to calculate the Reynolds number, and then we need to calculate the relative roughness, which is epsilon over D. So epsilon is the roughness of the inside surface of pipe, and D is the diameter. And then what we need to do is, for example, we calculate the Reynolds number. For example, we get the Reynolds number is 10 by the power of 4. What we need to do is we draw a straight line here, and then let's say our relative roughness is 0.02. Then we look at this line here, we take the intersection, and then we could assume the friction factor is around 0.034, let's say. So that's the way we determine the friction factor in fluid mechanics 1. And then if the velocity change, for example, so for example, the velocity change from 10 by the power of 4 to 10 by the power of 6 here. So then we do again the straight line. So if the relative roughness is the same, so we could say that the friction factor here is now changed into this number 0.025, for example. So we have two different friction factor when the velocity here is changed. Okay, that's what we learned in fluid mechanics 1. But in this subject, in this open subject, we would like to give you another perspective of the roughness. Okay, but if you see in transition region here, okay, if you see in turbulent region here, you will find that the roughness here is actually a straight line. So means that if your diameter is big, because we are now focusing on a pipe network, so if your pipe diameter is big, they will give you for sure higher relative roughness, because you could imagine there is a huge difference of roughness for pipe that you buy in hardware, I mean the PVC pipe, with ini bukan, ini dah masuk chapter 2. Okay, so ada orang tanya. Okay, so so if we see that if you compare, if you imagine the pipe, the roughness of pipe that install yang awak nampak pipe besar yang diameter dia mungkin 1 meter dan sebagainya, dia akan buat daripada besi. Okay, ada setengah aliran mungkin dia akan buat dengan campuran konkrit dan sebagainya. So roughness dia mungkin terlalu besar. So jadi roughness dia besar, diameter pun besar, dia akan menghasilkan kemungkinan menghasilkan relative roughness yang besar. Oleh itu, okay, so kemudian awak pun boleh imagine, if you could imagine that if the diameter is bigger, then it will give you a high Reynolds number. So what I want to say here is, for example, if the relative roughness is higher here, it will create a turbulent flow. So the region is now in this region. So let's say the velocity is 0. Okay, saya padam dulu lah. Okay, let's say the velocity is 10 by the power of 5. And then if we draw a straight line here. And then, for example, we are focusing on this, let's say this part. So the intersection here will give us a friction factor around here. So which is might be 0.038. Okay. And then if the flow rate is changed, the velocity is going down or going up. So we found that if the velocity is here or the velocity is here, they will also give us the same value of frictional factor. So means in pipe system, when the diameter is bigger, and then the roughness of the pipe is quite rough. So we found that the velocity that flow inside that pipe is not influence the friction factor. So jadi saya nak terangkan di sini, sekiranya aliran itu adalah completely atau fully turbulent, so kerana kita fokus kepada jaringan pipe. Jaringan pipe ni maknanya kita akan seolah-olah masalah kita adalah masalah daripada satu tangki air kat taman U yang akan kita distribute kepada perumahan di taman U. So kita bukan lagi memikirkan tentang tangki air yang ada atas ceiling rumah awak dan pipe dalam rumah. Okay, kalau yang itu mungkin pengiraan dia lebih kepada transition kat sini. Okay, maknanya antara complete laminar flow dengan complete turbulent. So sekarang ni kita fokus kepada masalah complete turbulent dengan keadaan pipe yang diameter besar, roughness tinggi. Okey. Jadi dalam keadaan tersebut kita dapati bahawa walaupun velocity berubah, kalau kita lihat di sini Reynolds number dia berubah, dia tetap menghasilkan nilai friction factor yang sama. Okey, so boleh nampak so maksudnya itu sebab kalau awak berbual dengan engineer yang terlibat dalam pipe air yang besar yang kat tepi jalan tu, okey, kita kata mereka tidak mengira velocity. Okey. Jadi apa yang mereka kira hanyalah kadar alir. Kenapa mengira kadar alir sahaja? Kerana perubahan velocity tidak akan mengubah apa-apa. Buktinya kita telah terangkan di sini. Okey, jadi oleh kerana velocity tidak memainkan peranan, kita kena kebanyakan ada engineers lah, kita fokus kepada Hardy dan Cross. Okay. Mereka mencadangkan bahawa kita boleh ubah equation untuk mengira losses. Instead of kita cari F, L over D, V square over 2G. So why not kita ubah V square tu, kita ubah kepada kadar alir. Kerana pengiraan kita lebih fokus kepada kadar alir. Dan secara realitinya, alat yang dipasang di dalam pipe yang besar macam itu adalah flow rate meter. Dia tidak mengira velocity air di dalam pipe, tapi dia mengira adalah flow rate. Okay. So berkenaan dengan nota ini, saya rasa awak boleh baca. Saya ada upload nota di dalam website. Dia lebih kepada keterangan yang saya ceritakan tadi. Okey, yang ini contoh berkenaan dengan losses ataupun nak mencari friction factor daripada sesuatu keadaan. Okey. So yang ini kita ulang balik sebab ini actually salah satu contoh pengiraan losses di dalam pipe. Saya skip aja sebab ini hanya pembacaan. Dia lebih kepada Manning, dia sama dengan cheesy equation, Manning equation. So yang ni ada Hazen-Williams equation. Dia akan lebih kepada, kalau awak tengok kat sini, ke arah mengeluarkan rumus yang menggunakan satu pemalar constant dan kita kira dengan menggunakan kadar alir. So yang ini sekadar nota. Okay. So ni Manning equation, kita telah bincang di dalam open channel. Okay. So saya harap awak dapat alert tentang perkara ini. Okay. Yang cuma yang saya nak cakapkan ialah, okay, ni minor loss. Okay. Saya rasa saya boleh skip yang ini. Okay, so yang tadi tu saya harap awak dapat baca, saya rasa awak boleh faham dengan mudah pengiraan tersebut. Okay, yang saya nak tekankan ialah sekarang ialah bagaimana untuk kita tukar equation major loss yang kita belajar sebelum ini kepada penggunaan flow rate. Cara dia mudah sahaja. Kita tahu sebelum ni head loss sama dengan F L over D V square over 2G. And now we try to change the terms of velocity here with flow rate Q. So what we did is, from this equation, so we could convert from the Q equal AV, then we substitute the value of A, the cross-sectional of pipe, which is circular, so it's pi d square over 4, and then we rearrange, and finally we could get the velocity square is equal 16q square over pi square and d by the power of 4. So, and then we substitute the value of v square here into this one. Okay, and then finally we could get this equation. Okay, so here if we enlarge this one, so we have HL is equal to F L over D by the power of 5. And then we have 16 over 2G pi square. And we have Q2. So here, okay, we could say that all of this parameter is actually fixed, constant. Because as I said, the pipe is all they will use the same type of pipe, so means that the friction here is constant, and diameter and also the length and the diameter is actually constant. So and then 16 2g and pi it also a constant. So the length here might be different according to one point to and 1 point. However, so in realistic, in pipe distribution, in water distribution or pipe network, so normally they will fix the length because, as you know, previously we say that the losses in pipe in this chapter is represent in pressure drop. So for SAJ engineers, they will create one pump house, or they will create another tank actually after a certain length, because when the pressure is continue dropping, so might be that that pressure is not enough to supply any water to supply water for the next taman perumahan. Okay, so jadi saya harap awak dapat imagine engineer bahagian air dia akan menitik beratkan pressure drop. Maksudnya after certain pressure drop dia akan buat satu water station. So water station ni sama ada dia buat satu lagi tangki supaya dia boleh ada pump, dia sedut pump tu naik atas satu tangki besar, and then dia akan alirkan semula. Itu sebab kalau awak tengok tangki air, Taman U ada satu, Pulai Flora ada satu, mungkin apa nama tu, Kangkar Pulai ada satu, Taman Teratai ada satu. Itu semua sebab kita kata walaupun ada satu tangki air itu mungkin berada tinggi kira-kira mungkin 20 meter daripada jalan raya, tetapi ketinggian itu kita kata pressure drop, mean losses yang ada di kawasan itu telah berkurangan dengan banyak kerana losses dalam pipe dan jarak pun semakin jauh. Mungkin dah ada 8 km, 10 km. So jadi pressure drop dah jatuh terlalu banyak. Jadi apa yang engineer air buat ialah dia akan buat satu lagi water station. Selalu dia orang cakap hin dengan water station lah. So idea dia ialah dia akan create satu lagi tangki. So tangki tersebut akan ada pump, so dia akan simpan air dalam tangki dan baru dia distribute ke kawasan yang lain. So yang sebenar kalau kita lihat secara meluas, kita akan dapat bahawa setiap tangki tersebut sebenarnya adalah network kepada jaringan air di Skudai. Jadi maksudnya sekiranya ada satu kawasan tangki rosak atau sebagainya, so air masih boleh disupply oleh tangki yang lain. Ini yang dinamakan pipe network. So kita dalam chapter 2 ini kita membincangkan perihal air yang mengalir dalam situasi yang lebih besar ini. Yang saya katakan, kita tidak sahaja fokus kepada bukan lagi fokus kepada sebuah tangki air yang ada dalam rumah, and then kita akan mengira losses dan sebagainya. Okay, oleh itu, okay, and then we could say that all this parameter is actually constant, then we name this parameter as K. So this is the common terms here. That's why now we get the turbulent flow equation for losses is HL equal K times Q square. Okay, sampai sini boleh ke?
Boleh Doktor.
Okay. Okay, then here in this notes, okay, I would like to share with you the difference, so the types of pipe connection. So we have two types. One is in series and one is parallel. So I think you already know about this in fluid mechanics 1. So I just to remind you. Okay, we do a revision about this. Okay, if the pipe is connected in series, so means that we have one type of diameter here, and then it's connect with another type of diameter, and then it's connect with another type of diameter. What we need to know is first the flow rate here. So the flow rate will remain constant at any point in the series pipe. So mean the QA here, okay, will equal to QB here, will equal to QC at this point. You could imagine that. So because the water is flow in one straight line, so the flow rate must be constant. However, so the losses here, okay, is actually increased depend on the length of the pipe, because when the water flow at water flow at A section, so they will have HA here. The losses is HA, and then when the water flows at section B, so the losses is HB, and when it's flow at section C, so the losses is HC. Now the total losses will become HA plus HB and HC. So and then if we convert it into the new equation that we developed previously, losses is K times Q square. So we could write this equation. So I hope you could understand this one. So and then, okay, so if pipe is connected in parallel pipe. So for example, we have one major pipe here, and this major pipe is distributed into three channel, three pipes, and then again it will merge in the output here. So let's say this is input and this is output. Okay, the major thing that you know that you need to know here is flow rate for input must be equal to flow rate for the output. Okay, however, the flow rate for each section here, section 1, section 2, and section 3 is actually the distributed value. So it will comes for equation of this one. So mean that Q in or Q out is equal actually the sum of Q1 plus Q2 and plus Q3. Okay. Because you could imagine that if the water flow is here is 10 liters, and then if it distribute into three different pipe here, so might be it is 3 liters here, 4 liters here, and another 3 liters at the third pipe. So it is the summation, the total of the input flow rate. Okay, however, okay, we could say that because the pipe is connected in parallel pipe, we could imagine, we could assume that the losses for each pipe is actually equal to each other here. So mean that losses for pipe number 1, pipe number 2, and pipe number 3 is actually equal. Okay. Okay. However, if you do experiment about this, so why we assume it is equal? Because normally if you distribute pipe, you will use same type of pipe. Okay, but if you do some kind of weird experiment, for example, you are connected with one with a PVC pipe, another one it might be with the concrete, with the very rough flow and so on and so forth. Yes, it will affect the flow rate. They will affect the flow, because the resistance, the losses is quite different. Okay, but if you just use three same type of pipe, So inshallah, we could assume that the losses for each pipe is almost the same. Okay, that's the idea of for the series and the parallel pipe. Okay, then I would like to propose to you the calculation for the losses, because previously in series pipe we could calculate the total losses by using this equation, and this equation is quite linear, means you could get this one. However, for parallel, the equation will look like this. Okay, it's happened why? Because uh, here we know that the losses can be simplified as K, Q, and square. So, and then the Q here is HL over K. So, if the QA here, okay, QA here is equal to Q1 plus Q2 plus Q3, we could have equation for losses as this one. So, H1 over K1 square root. And then if you do all this, you simplify all this uh, calculation, you could say that the final equation that normally appear in textbook is this one. So this is the equation for us to simplify the resistance of parallel pipes. I will show the calculation later on. So we learn about the theoretical first. So here, so I hope you could understand the idea of Moody chart, and then we know there are, when complete turbulent, the velocity is not affected the friction factor anymore, so we change the calculation into losses equal K times Q square. Okay, and then in last 3 pages note here, so we discuss about how to calculate the total losses, mean K, in parallel and series pipe. So I will show you the question later on. So we go for this one. We go for the theoretical first. Okay, then. So I think I already upload these notes too. So this is the notes for the Hardy cross method. So you could read all of this. So so the idea of Hardy cross method is, okay, we want to calculate the flow rate. We want to estimate the flow rate for pipe network. So what I call for what you need to know about pipe network is, okay, when we have, for example, we have a water station here, A, B, C, and D, and then the water is coming, and then the water will out, for example, and another source come works act as input and output. Okay, and then the idea of Hardy cross method is, okay, so it proposed, or he proposed that if you have a network here, so and then the calculation of losses must be the same if we calculated it counterclockwise or clockwise. So for example, if we are focusing on this one, okay, if you are focusing on this one, if we calculate the losses here plus here plus here plus here, it must be equal to the losses from here to here to here and to here, because losses is not a vector, so the direction of losses is actually not affected the calculation. Okay, however, we could simplify this one by saying that, okay, by saying this statement, head loss in pipe BA, okay, plus head loss in pipe DC, so is equal actually at the head loss in pipe AC and head loss in pipe BD. Okay, okay, so this is the first assumption, but the idea is, okay, for example, if you have a pipe from here to here to here and to here, okay, the total losses here is actually equal if you do it at any direction. Okay, so for the network, so let's say we have a lot of water station here. So if you calculate the losses here, then the losses at inlet here. Okay, and then, and no, if you have one water here, so if the water is flow like this in circulation, okay, whether it is counterclockwise or clockwise, so the calculation or the amount of losses will be the same. So this is the first idea. And then the second idea that you should know is for one single point, for one single water station here, okay, the conservation of flow rate must be conserved. Okay, so the idea is the total inlet must be equal to the total outlet. So whether, for example, you have one water station here, if the inlet is 3 and let's say the outlet is 2, okay, so it's not about the quantity of the outlet and inlet and outlet, but the quantity of volume flow rate. So for example, if the volume flow rate is 2, 3 and 4, so the total here is 9 meter cube per second, for example. So, and then if you have only 2 outputs, so you must make sure that this output will has this output will have 9 meter cube per second. So might be this is 4 meter cube per second and this is 5 meter cube per second. So this is the two basic idea proposed by Hardy-Cross method before they propose the equation for calculating the Hardy-Cross method. So, and then, okay, so I hope you can understand. First is the total of the losses in pipe network is the same, whether you calculate it counterclockwise or you calculate it clockwise. And then the total flow rate must be equal for one single point, for one point. So the total inlet must be equal to the total outlet. Okay, so this is the calculation. So I think this is already uploaded in my notes. Okay, but I'm going to explain it here. Okay, we know that the losses from the Bernoulli equation, from what we learned in fluid mechanics 1, can be simplified as K times Q square. So as I said that we need to calculate this one, okay, in clockwise and counterclockwise. So here, if the clockwise, so the symbol is HC, and then it can be written as KC times QC square, means KC is the coefficient of losses for clockwise and QC is the flow rate for the clockwise. So, and then if we calculate it in counterclockwise, so we could write this equation. So we have HCC equal KCC times QCC square. So as I said, okay, here at this paragraph, so the total losses, whether you are calculated in clockwise or counterclockwise, so the amount must be the same because we are calculating on the same on the same device. Okay, now, so, and then from here, okay, and then what you need to do is, for example, we start with a try and error. So, and then, for example, we get some value, and for sure, for the first trial, the value is not correct. So what we should do is we need to take some amount from the certain part and then we top up to another part. So idea dia ialah kita kena pastikan bahawa total losses untuk clockwise mesti sama dengan total losses pada counterclockwise. Okay, katakan kita buat try and error method. Kita beri satu nilai dan kita buat. For sure nilai yang kita beri sebenarnya tidak seimbang. So jadi apa yang perlu kita buat? Kita akan ambil sedikit daripada nilai yang banyak dan kita akan pindahkan ke nilai yang sedikit. Kita akan balance macam awak nak buat timbang. Kalau dia terlebih banyak, ambil sikit letak kat sebelah yang satu lagi. So supaya dia balance kan. Okay, itu yang kita buat. Jadi kita imagine, okay, first step we imagine that our prediction in clockwise is a little bit bigger. So what we should do is we deduct the amount of flow rate here with delta Q. And then we add this delta Q to the left hand side equation. Awak tak boleh letak delta QC, delta QCC. Kerana apa? Delta Q is actually same amount. Dia adalah satu nilai yang sama. So means that we deduct a little bit from the clockwise calculation, and then we add the same amount here at the counterclockwise calculation. Now, we hope this will balance the equation. Okay, lagi satu yang selalu kesilapan pelajar ialah awak kena menulis KC. Okay, the amount of KC and KCC here cannot be deducted. And then the way you deduct this value is you deduct with in the bracket. So awak kena buat QC tolak delta Q dalam bracket kuasa 2. Ada pelajar tersilap, dia buat QC kuasa 2 tolak delta Q kuasa 2. Okay, so boleh nampak So and then if we expand this equation, so we have this equation, and then this is the tricks. Okay, because delta Q square is very small, so we could neglect it, and then we could rearrange this equation with delta Q equal total of KC QC square minus sigma means total of KCC times QCC square and so on, like this one. Okay, so and then we could simplify this equation by using the idea of this one. So we assume that HF is KQ square and KQ can be written is HF over Q. So KQ here is actually from here also. Daripada yang ini, kita bawa satu Q duduk bawah. So jadi kita kata KQ equal HF over Q. And finally, you will have this equation. Okay, so kita akan dapat delta Q. Okay, kita akan dapat delta Q equal total losses for clockwise minus total losses for counterclockwise divide by 2 times, so ini ada bracket, 2 times total losses counterclockwise divide by clockwise divide by flow rate of clockwise plus sigma total of losses for counterclockwise divide by flow rate for counterclockwise. So I hope you need to understand this equation. You need to understand and remember this equation. Okay, and then the idea is, okay, I will show you how to calculate this one from this below example. But we stop. I would like to stop here because the time is over. Okay, so the idea is we will calculate by using the idea of trial and error. We need to we need to determine the value of delta Q. And delta Q is not the answer. Delta Q is the indicator whether our answer is accurate or not. The smaller the value of delta Q means your balance is good. So for example, if the delta Q is 5 meter cube per second, it's quite big. Okay, so so if your delta Q is very, very small, for example, is 1 liter per second or 0.1 liter per second, so means that you are now successful to balance the clockwise and counterclockwise value.